Okay, again, I apologize for the change in order, but we're going to go ahead and start Chapter 4. We'll learn all of Chapter 4, review, test Chapter 4, and then give you a chance to go back, ask any questions on Chapter 3b that you need to before we look at that test. Midterm went really well. Thanks for your patience. Hopefully I will be back soon. Sections 4.2 and 4.3. So again, we're starting Chapter 4, but we do so out of order. I think it makes sense for you to understand what we're finding and what everything actually means before you figure out just the formulas and the rules. So your essential questions, you have a lot of space because today you're going to be asked to find lots of different sums. So your essential questions are, how do you find 1, an upper sum, 2, a lower sum, 3, a left-hand sum, 4, a right-hand sum, 5, a midpoint sum, 6, a trapezoidal sum. And that will be what we cover today. The other essential question will be, how do you find an integral with signed area? And we'll deal with that in our second day for 4.2 and 4.3. Excuse me. Objectives are that you have to be able to find any Riemann sum. A Riemann sum is one of the 6 types listed above. And then second piece would be on the second day that you can integrate with geometry. Alright, so we're going to start talking about how to find area under a curve. And that is our ultimate goal for today, is really understanding that idea. And in order to do that, we're going to take a curve and we're going to start to use some rectangles to make that happen. So in order to approximate area under a curve, we could inscribe rectangles, putting them underneath the curve, or we could circumscribe rectangles, putting them above the curve, finding areas of those rectangles, and then talking about needing summations. If you took the areas of those rectangles and added them up, that would be our area approximation. Now, the image that you've seen right now, it's not the best approximation because, for example, all this is extra. It's above the curve. It's too much. And then in this other one, we have all this space that's too little, all this extra white space that's left underneath the curve. So by adding up the areas of those green rectangles, sometimes we get too much of an approximation, we get an overestimate. Sometimes we get too little of an approximation, we get an underestimate. But our process would begin by subdividing our interval AB, so assuming this is A in our picture, and this is B. and A and B. Subdividing our interval AB into n subintervals of equal width. Well, if you wanted to make them have equal width, so AB into n subintervals, but they have to have equal width. Well, to do that, you would take your whole distance, B minus A, and then you would divide by n to cut it up into n pieces. So the width of each rectangle, then, we would denote it by delta x because you're measuring across the x-axis, so the change in x. And you find it, again, by doing B minus A all divided by n, the number of rectangles that you want. Okay. What you are looking at right here showcases a couple of different terms from the front page. So this is an upper sum simply because it's an overestimate. This also coincidentally happens to be a right-hand sum because all the heights are coming from the right endpoints. So if I look at from here to here to here to here to here as my divisions, and I need to make a rectangle each time, the rectangle for the first one comes from the height on the right side. The rectangle for the second one comes from the height on the right side. The rectangle for the third one comes from the height on the right side. And the rectangle for this last one comes from the height being on the right side. So anytime you hear a right-hand sum discussed, it just means you have to use the right side to make the rectangle heights. Anytime you hear an an upper sum discussed, you have to make sure that your rectangles overestimate or are bigger than your curve. Sometimes those two things would go together, upper sums and right-hand sums, and sometimes they would not necessarily. You just have to know the terminology for each. And it would depend on whether your function was increasing or decreasing, and we can talk about that. Then some more terminology. You could have a lower sum. A lower sum just means that you need it to underestimate. So you just need rectangles that are always too little. Or you could have a left-hand sum. And the left-hand sum just means that your heights have to come from the left endpoint. So if you take this, here's my division, 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 and you go up to make a rectangle. This rectangle came from the left-hand side being the height. This rectangle came from the left-hand side being the height. This rectangle came from the left-hand side being the height. And this rectangle came from the left-hand side being the height. When you're making the rectangles, you always find your division and you have to trace up until you meet the actual function. So like here's our function going through. If you notice that the rectangles always met the function here and here and here and here, in this case on the right side to be too big. But over here, here's our function. And when you're making your rectangle, you have both sides of it, the left side and the right side, and you decide, in this case to be a lower sum, you would go up until you meet the function on the left part of your rectangle and then go over. But you're going up to the function height at some point. Okay? And then this just kind of sums up what we've been talking about. Right and left-hand sums can be either upper or lower, or they could be neither. It could be mixed up. And you'll see an example of that down below. Don't think that they always have to go together as pictured. So just make sure that you know the four terms, the definitions that are in the small print below. That's what defines an upper sum or a right-hand sum, etc., etc. So let's take a look at a picture that mixes some of them up. So in this particular case, right here, these are all upper because they overestimate. They're all too big. And they happen to all be, I want you to take a look and decide if you think they're left or right. So from here up to the function and over, from here up to the function and over, from here up to the function and over. They all happen to be left hand. Okay. However, if we take a look over here, these are still upper because they're an overestimate, and that's what it means to be an upper sum. But if you take a look and decide as far as where the rectangle goes, going up to the function and over, going up until I hit the function and over, these happen to be right hand sums. So in your initial definition, the upper sum went with right hand. But in this picture, you've seen an upper sum that happens to be left hand and an upper sum that happens to be right hand. So some connections we've made depending on whether the function is increasing or decreasing. If the function is increasing, your upper sum, so looking at the right piece here, the one we just did, that was an increasing segment, and to get an upper sum, it happened to be the right hand sides. So you would use the right ends. And if you had an increasing function and you wanted a lower sum, you could draw out an example of that, but it would turn out that you would want to use the left. My pen is not very good, sorry. And for decreasing, if you wanted an upper sum, so that's what we started with in this example down below. Over here on the left, we had a decreasing part of our function, and to get an upper sum, you would use the left hand endpoints. And you could also make up an example and see that to get a lower sum, if you have a decreasing function, you would want to use the right hand endpoints. You need these kinds of things for AP questions when they'll ask you to match something up. But for example, all they'll tell you is that like f prime is negative, so all you know is that f is decreasing. And then you have to go from there to make your other decisions. Okay, before we get into that, let's take a look at some more ideas of what's going on. So based on what we talked about, it should be clear that this little s, and the little s just represented the lower sum, should be smaller than the actual area, and that the actual area should be smaller than the capital S, which represented the upper sum. And that's not like a universal symbol, capital S and lowercase s. It's just one that our book happens to use. For AP, they'll actually write out the term upper or lower. But it should make sense that the lower sum should be too small, the actual area should be in the middle, and the upper sum should be too big. Okay, well, it turns out if you have a function that is continuous and non-negative, it always stays above the axis, then we have a better way to write the actual area. The actual area can be written with this symbol, and how you would read it, you would say that this is, let me get another pen so I can write it. This would be called the integral of f of x from a to b. The integral symbol kind of looks like a stretched out S, and that makes sense as far as standing for summation. But it's just elongated a little bit if you want to kind of practice drawing some of them. Okay, this is what we call a definite integral, and it's a definite integral because of the bounds A and B. We will see something called an indefinite integral later in this chapter, where there will not be any numbers on the bottom and the top here. So our lower limit is a, and our upper limit is b. So we start at a and we progress to b. Okay? This is what we call a definite integral because it has bounds. And again, if your function is not negative, it always stays above the x-axis, then the area that we're finding, not the approximation of it, but the exact area, would be equal to this integral. Okay, then we're going to move into a theorem and talk about, well, hey, we started off with all these rectangles, and we know that they're not accurate. If you flip back to your last page, you can see that sometimes they had extra stuff that we had, sometimes they had white space that they left if they were too small. So they're definitely not accurate. And we want to start trying to think about how they could be more accurate. Well, it should make sense to you that they could be more accurate if, so remember from the last page, n was our number of rectangles. So if you let n go to infinity, that means you take an infinite number of rectangles. If you take an infinite number of rectangles, then it should make sense to you that as you take limits, the lower sum and upper sum limits should be equal to one another if you have an infinite number of rectangles, because it should turn out to be that the lower sum limit and the upper sum limit, if you have an infinite number of rectangles, would actually equal actual area. They would be perfect. They wouldn't be too big anymore. They wouldn't be too small anymore because you would have so many rectangles in there that your error would go away. So it's just connecting these ideas. So you had from up above that the lower sum was smaller, then you had the actual area, then you had the upper sum. Well, now this is saying if you take limits of each of those and you find that they're equal, if you remember the squeeze theorem back in chapter 1, you might have to go back and review your notes, but if you have this inequality statement that is true and it turns out that the limit on the left side is equal to the limit on the right side, then that means it's equal to the limit in the middle. It squeezes it into the middle. So it helps you make this connection that this is the actual area. Helps you make the connection that it's the actual area. Okay. In that case, that means if you're going to take infinite amounts of rectangles, then you could choose right or left. You could choose either lower or upper because it's not going to matter, because if you have infinitely many of them, you're going to get the exact area. Okay, that was a lot. Just like in most things we learn, you have all the theory parts and your definition parts, and then we have to figure out what it all means. So let's start taking a look at that. They want the lower and upper sums for the region bounded by the function x squared and the x-axis on the interval 0 to 2 using n equals 4. Well, let's draw that out, and you have a lot of space. I'm going to draw it out once up above so that we can do our lower sum, and then once down below so we can do our upper sum. This is just a parabola. It's got a vertex at 0, 0. N being 4 means we want 4 rectangles. N equals 4, 4 rectangles of equal width. So to figure out how wide they are, that delta x part is just going to be the 2 minus 0, because that's how long the interval is, cut up into 4 pieces, divide by 4. So each rectangle is a half a unit. Okay, so I need to make 4 little divisions, 1, 2, 3, 4, and end up at 2. So a half, 1, 3 halves, and 2. And I need to figure out where I am on my function. So this is the x. My function is x squared. Well, at 2, I'm up at 4. I'm not going to scale these the same. I'm just going to make 4 tick marks and count by 1s there. So 2, 4, 1, 1, 0, 0, and you need to draw your parabola. Mine's not the best on this little tablet, sorry. Okay. Then we need to go back and remember how we find areas of rectangles. So area of a rectangle is just going to be base times height. Well, in our case, the base is going to be delta x, and the height is going to be a function value, because you're going to have to go up to the function to make your rectangle. So let's see what that looks like. If we want to do the lower sum, the little s, well, then for my first rectangle, it would be choosing between the 0 and the half. Draw up until you meet the function. Well, at 0, 0, you meet the function. And then at 1/2, 1/4, you meet the function. Since you want a lower sum, you want the smaller of those. So you're actually not going to make a rectangle. It would be just going straight across from the 0. So that area would be 1/2 times f of 0. Plus, for the second rectangle. So now, between 1/2, go up to the function, and 1, go up to the function. Which one is smaller? Well, you get the smaller height when you're at the half, so go over there, and that makes your second rectangle. And that came from the height of f of 1/2. So the width is a half, because all the widths, all the delta x's are a half. And the height came from f of a half. Plus our third rectangle. Go up for the 1, then go up for the 3/2 till you hit the function. Which one is lower? Because we're looking for a lower sum. It's lower when I'm at 1, so I go across. So the width, again, of every rectangle here is a half. And the height that I just used came from f of 1. Plus, and now our last rectangle, go up with the 3/2 and go up with the 2. Which one is lower? It's lower when I'm at the 3/2, so go across there. So a half for the width, and then f of 3/2. And then we could go figure that out, because we know what the function is. It's x squared. So this would be 1/2, and 0 squared is just 0. Plus 1/2, and 1/2 squared is 1/4. Plus 1/2, and 1 squared is 1. Plus 1/2, and 3/2 squared is 9/4. If you were computing this by hand, a strategy would be to factor out the 1/2 probably, since it's in common. This math's pretty easy. It cleans up to be 7/4. And in this case, we are measuring area, so it would be 7/4 square units. You're not always going to be measuring area because your graph's not always going to be above the x-axis, but for right now, it does match up. So our lower sum because they asked for an upper and a lower, our lower sum is 7/4. In this particular case, our function was always increasing on that interval. So on that interval, a lower sum happened to be left or right. Well, if you go look at where the heights came for all those rectangles, they all came from the left side of the rectangle. So it happened to be a left sum, left hand. sum. Okay, we need to redraw the same thing and do an upper sum. So if you redraw your image, 4 dividers, 1/2, 1, 3/2, 2. Counting by ones here, so at 2, 4, at 1, 1, and 0, 0. That's terrible, connect the dots, sorry. It should be a parabola, but this tablet's kind of hard. Okay, then I want an upper sum. So every single time I go over, so between 0 on the function and 1/2 on the function, which one is taller? It's taller at 1/2, so that's what I use for my rectangle. So 1/2 wide, in this case, times f of 1/2, plus, now between 1/2 and 1, go up to the function, which one's taller? It's taller at 1. So 1/2 for the width, and then f of 1, plus, now between 1 and 3/2, which one's taller? 3/2 is taller. So 1/2 for the width, f of 3/2. And lastly, between 3/2 and 2, which one's taller on the function? It's taller at 2. So width is 1/2, and you're going to use f of 2. And then again, same computation skills that we talked about above. You'd go up to the function tells you to square everything you put in, so you'd square everything you put in, add everything up. You would get 15/4. Since this is all above the x-axis, this is an area measure, so it'd be 15/4 square units. Okay, and that is our upper sum. Again, for AP, the capital S and little s isn't going to mean anything to them. They're just going to come out in words and ask you for lower or upper or left or right. And if you take a look at the graph here and try to decide, since our function was always increasing, it's always going to either be left or right hand. It's not going to switch over in the middle. If you take a look at all those rectangles, those were right-handed rectangles. Okay, so you never know what terminology they're going to use. And if we want to connect to the whole inequality part that we saw on the last page, we would see that actual area should be stuck in between the lower sum, which we came up with as 7/4, and the upper sum, which we came up with as 15/4. And you guys on your calculators, on your TI-89s, under F3, you had an option for differentiate. You also have an option for integrate. So actual area would be if you let n go to infinity, and we would start to use the integral symbol. So it's like that stretched out s. The integral from 0 to 2 of f of x dx, that's that differential notation from 3.9. It's just our way of telling you that you're integrating with respect to x. So the integral of f of x dx turns out to be 8/3. And you can see that that is caught in the middle of 7/4 and 15/4. Okay. Next idea. So we've talked about lower and upper. We've talked about left and right. We had 6 things on the front. The 2 that we are missing still are midpoint and trapezoidal. So the midpoint rule tells you that you're going to use the midpoint of the subintervals to get the heights. So instead of the left side, instead of the right side, you use the middle. So what that looks like when you're drawing this out is you would go, so here is a division. Instead of going up to the function on the left or the right, you go in the middle of it, go up to the function, and go over. Here's another divider, here, And here, instead of using the left or the right to go up to the function, you take the middle of it, go up to the function, and that's your height for your rectangle. Again, let me switch colors. So here and here, instead of going from the left to the right, take the middle up, and that's the height for your rectangle. Again, instead of left, instead of right, take the middle up until you touch, and that's your height. Typically the midpoint, just you can tell by looking at this image, is a little more accurate because yes, it has a spot that's above, like right here, but it's usually counterbalanced pretty well with the area that's below, and so it's a better estimate of area. Excuse me. Alright, sorry about that. Okay, so if we want to approximate the area bounded by this cubic function and the x-axis on the interval from 0 to 1, using midpoint rule with n equals 5. So n equals 5 tells us that you want 5 equal width rectangles. And so if you want to figure out how wide they are, delta x would be the whole span of your interval, which is from 0 to 1, so 1 minus 0, over, cut it into 5 pieces, so 1/5. They can make this trickier on you because you might not always start at 0. Your interval might go from 1 to 5, so then it would be 5 minus 1 over something else. Okay? And midpoint, since we want midpoint, you need to find the midpoints of the subintervals. Well, if each one is 1/5 wide on its own, and you want the middle of it, you need to take half of a fifth. So the heights are going to come from little increments of 1/10. And we'll see that in a second when we draw it out. As far as knowing what this function is doing, that's a little more complicated because your cubic function, it's a cubic, it has a negative leading coefficient of -1. So it's going to go down on the right side. Since it's cubic, it's going to go up on the left side. It's some kind of image like this, and you need to decide what piece of it you're seeing from 0 to 1. So if you want to find its x-intercepts, you could set the whole thing equal to 0, take out an x, and you get 2 minus x squared. So it crosses the x-axis at x equals 0 and plus or minus radical 2. So 0, and then radical 2 is like 1.4-ish. And then negative radical 2 would be negative 1.4-ish. So as long as you figure out, since you're only looking from 0 to 1, you want just this little region right here, right in there. So as long as you figure out just where it is at 1, if you find out it's above the axis at 1, you know it's going to stay above the axis the whole time because the only time it's on the x-axis is at 0 and plus or minus square root of 2. So those are some algebra things that you might have to remember. So f of 1, just to double check, we would have 2 minus 1 is 1. So at 1, you're at 1. It's going to stay above the axis the whole time. Okay? It's actually going to be this part that's curving like that. Alright, so if we draw out what we've got, you need quite a bit of space because you have 5 rectangles and we want to do midpoints with them. So I'm going to put my mark for 1 way over here. I'm going to make my little intervals. Okay, so here's 1/5, 2/5, 3/5, 4/5, and then 1 is at 5/5. Okay, then we just checked it's at 1, 1. I'm going to try to make this to scale just because we've got so much we're trying to fit in. So here's 1, 1 and 0, 0, and it's that part that's going like that. Sorry, this is a bad drawing on the tablet, but close enough. Okay. Then for midpoints, I want to take this space between 0 and a fifth, and instead of going up from either of those heights, I want to go up from the midpoint at a tenth. So cut it in half, mark a tenth. That's where you go up to your function, and that's where you draw over your rectangle. Then for the next one, so I need to measure and kind of count by tenths. Well, 1/10 and then 2/10 is the same thing as 1/5. So the midpoint of that next rectangle is going to be at 3/10. And that's where you go up to the function, and that's what you use to come over and make your actual rectangle. And then 4/10 is the same thing as 2/5. 5/10 would be halfway in between the 2/5 and the 3/5. Go up till you hit the function, and then go over to make your rectangle. So the initial subdivisions where you marked your fifths, sorry, that's terrible, the black parts, those should be the sides of your rectangle, but the height is coming from the midpoint. And then if you keep counting, so we had 5/10, then if you count 6/10 would be the same thing as 3/5. 7/10 would be in the middle, and go up till you hit your function, and go over. And then 8/10 is the same thing as 4/5, and 9/10 then would be in the middle for that last part. Go up until you hit your function, and then go over. Okay, so we have all our rectangles, and really now all we're doing is just adding up the areas of the rectangles. A good check is to double check, so we verified that 1 is the same thing as 5/5. It's also the same, we were at 9/10, the next step would be at 10/10, and yeah, that's the same thing as 1 as well. So our counting all worked out. So I have 5 rectangles, but for the heights, instead of using the left side or the right side, I use the midpoint. So the midpoint sum would be, each of them have a width of 1/5. So 1/5 wide times f of, for the first one, I got the height from 1/10, plus 1/5 wide, and for the second one, I used f of 3/10. And for the third one, 1/5 wide, I used f of 5/10 for that third rectangle, plus 1/5 wide, and I used f of 7/10 for the fourth rectangle, plus 1/5 wide, and I used f of 9/10 for the last rectangle. Okay. Figuring out this would be a little more frustrating with the 2x minus x to the third going back to this function. It would be frustrating by hand. Could they make you do it? Maybe once, yeah. But this would be, feel free to use your calculator to add up those computations. And like we talked about, it might be easier for you to just factor out the 1/5 and then add up all the function heights. That's fine too. But you should come up with 151 over 200, which as a decimal is 0.755. Since we know our function is above the x-axis the whole time, this would be in square units. This is area. But again, that's not the case if your function is not always above the axis. And you'll see more complicated examples in later sections. To figure out exactly what it is, exact would be having an infinite number of rectangles, and our representation for that is the integral symbol, and our lower bound goes on the bottom of 0, our upper bound of 1 goes on the top, and then f of x dx to say we're integrating with respect to x. That turns out to equal 3/4. You can see that the midpoint is pretty darn accurate. So just by adding up those 5 rectangles, 5 isn't even that many, we got an area of 0.755. And the exact area, if I go up, I wouldn't color this in if I were you, just because it'll be hard to read your notes later, but the exact area of this black part all under the curve, the exact area of that is exactly 0.75. And I came up with 0.755 by adding up 5 rectangles. So midpoint is pretty accurate. For Riemann sums, the term Riemann sum just means it could be an upper sum, lower sum, left-hand sum, right-hand sum, midpoint sum, or trapezoidal sum. That's all the Riemann sum means. But something important for you to pay attention to is that the intervals don't have to be of equal widths. So pay attention to the problem. If they tell you that like n is 5, that is their way of saying that they want 5 equal width rectangles. But if they just say that we want you to use some other intervals, or they give you a table and they're not equally spread apart, it's okay. They don't have to have equal widths. Okay, so we've seen a couple examples. Before we take a look at trapezoidal rule, let's take a look at one that does not have equal widths. And this wouldn't be a bad idea to pause and see if you guys can figure this one out on your own from the table of values. So the function f that they're showing us is continuous on the closed interval from 2 to 14. So for the span that they're showing us, we have a continuous function, and it has the values that they're giving us. Using the subintervals 2 to 5, so here to here, and then 5 to 10, so here to here, and then 10 to 14, so here to here. They want you to calculate using a right Riemann sum. So again, just remembering the right tells you that the heights are from the right ends. Okay, well, so from 2 to 5 here, the delta x part is 3. You went up by 3 units. Which side would be the right end of that interval? So left would be 2, right would be 5. So this would be your height. So if we're going to add up our right-hand sum, the width for that first one would be 3, and the height for that first one would be 28. Okay, then I need to add up the second one. Well, from 5 to 10, the delta x, the width, would be 5. And then the right-hand side, 5 would be the left, 10 would be the right, so the height for that would be 34. So 5 for the width, 34 for the height. And then I need to add up the last one, going from 10 to 14. Delta x this time would be 4. And then between 10 being the left-hand side and 14 being the right-hand side, so my height would come from the 14. My height would be 30. So again, width is 4, height in that case is 30. In this case, you don't have a width or a delta x that's the same every time that you're going to factor out. So you're just going to have to do each of those computations. And you might have to go over to the side of your paper and actually multiply everything out. It could very well be a no calculator question. You should come up with 374. So answer would be D. You can graph. You definitely don't have to. But you can graph them out and draw out what that looks like, where you would have like from 2 to 5. So say here's 2 and then here's 5. And you could plot at 2, it's at 12, and then it jumps up to 28. So from 2 to 12, and at 5, it's at 28, and the right-hand side would come from using the 5. So you could draw out that rectangle and then keep going and draw out the other rectangles that you have. You definitely don't have to graph them. Okay, the only one of our 6 that we have not done is trapezoidal rule. And so that's going to be, instead of making rectangles, you're going to use trapezoids. So you're going to draw trapezoids inside your shape. Well, it might take some remembering, but the area of a trapezoid is 1/2 times the height, and then you add up the bases, b1 plus b2. Well, you have to remember that the bases are parallel, and that the height you get from a 90-degree angle with the bases. Excuse me. Alright, so let's take a look at what those look like. So a trapezoid, here's one example. Let me try the green since that's a color that's not already used here. So we have lots of different trapezoids that are shown. Let's look at, like, here's one. Oh my gosh, sorry. I'm not drawing on this very well at all. Here's, sorry, let me erase. Connect the dots right there with a straight line. There you go. So there's a trapezoid. And base 1 would be that first vertical segment, and base 2 would be that second vertical segment. And if you kind of tilted it down here, so and drew it like this, here is your 90 to make your height, and here was B1, and here was B2 going all the way across. And then in your next example, B2 gets reused again and goes over here to B3. And so if you folded that one down, you would end up with this kind of shape. Oh my gosh. I apologize for my wonderful drawing skills on this board. But these sides are parallel. This would be your B2, and this would be your B3. And here's your height from your 90. Okay. If you notice, your bases are what we've been referring to as like heights of rectangles. So your bases would come from function values. These bases would come from function values. And then in this case, your height is actually the delta x part, how wide each of them are. So again, height for a trapezoid is always from a 90-degree angle between the bases. And so in that case, when we're looking at a function example like this, the heights are going sideways to make that 90-degree angle. Okay? Alright, something that you should pay attention to. So we had tangent lines tied to concavity based on if your function was concave up, tangent lines were underestimates, and if your function was concave down, tangent lines were overestimates. It turns out there are some connections you should make for trapezoidal rule with that. So let me use some colors I have not used before. your trapezoids will underestimate your area when your function is, we'll take a look at which trapezoids are too little. That would be this first set that we had right here. Those trapezoids were too little. They were under. They would be lower. Okay, so underestimates, and if you take a look, it's when your function is concave down. It actually doesn't matter regardless of increasing or decreasing, because you can see that here is a space where my graph is increasing and my trapezoid is still too small. And when it switches over and it starts to decrease, my trapezoid is still too small because I'm concave down. And then another color that I haven't used, I guess we haven't used black here. If you take a look right here, you can see that those trapezoids are over the graph. And so trapezoids overestimate when you are concave up, regardless of whether you're increasing or decreasing. If you take a look at this segment, I'm decreasing in concave up and my trapezoid's too big. Now I'm increasing in concave up and my trapezoid is still too big, regardless of increasing and decreasing. Okay? So those are relationships you've seen just from other AP examples that you know you're going to have to use. Let's take a look at how this applies when we look at tables of values, and then how it applies with those connections about overestimating and underestimating with trapezoids and with like left and right hand sums. Again, you kind of want this image in your head that our heights were coming from the delta x, or the width. Oops, sorry, that's a terrible highlighter. It's not big enough. We were using delta x for the height in the formula, and we were adding up the bases with the function values. And then there's always just a half that's part of the formula. So if you go take a look, here's a table of values. And again, for Riemann sums, they don't have to be equal widths. These happen to be. So if we read this question, we have a continuous function f. They tell us that we're using equal subintervals, 4 equal subintervals from 0 to 2. So if we draw those out, here's 1, here's 2, here's 3, and here's 4. And every single time delta x is 0.5. They were always 0.5 away from each other. Okay. Which of the following is the trapezoidal approximation of, this would be the integral, with the trapezoidal approximation of the integral from 0 to 2 of f of x dx. They're automatically assuming that this function is going to stay above the axis the whole time when they're asking you to approximate the integral. I mean, you can go with that because they're giving you a multiple choice question, but in some of their trickier multiple choice questions, you might not always want to assume that just because the values you see are positive, what if at 0.25 it dipped down below and did something funky? But here they're telling you to approximate it with the table that's shown, so all you have to go off of is the table that's shown. And so in our case, you can draw it out if you would like to, but we are using the idea of a half times the delta x for the height times the function value sums. Because the delta x was our height, and the function values were our base 1 and base 2 that we were adding up. So the integral from 0 to 2, and again it's like a stretched out s, of f of x dx, that just tells us that we're integrating with respect to x, is approximately equal to a half, because it's a trapezoidal rule, then times our delta x, which is always 0.5. Then times our base 1 and base 2. In our first example, here's base 1, here's base 2. So you would add up 3 plus 3. And then in our next case, we wanted 4 trapezoids, so a half because it's part of the trapezoid formula. Then delta x is a half because they're all a half apart. Then I need to add up the function values. Well, in this case, between here and here, I would use base 2 and then base 3. It would get repeated. So 3 plus 5. And then plus a half, because it's a trapezoidal rule, times a half, because delta x, they're half apart, times function values. And so from here to here, I would use base 3 and base 4. So I would add up 5 and 8. And then plus a half, because it's trapezoidal rule, a half, because the delta x is a half. And then I need to go add up the function values for those bases. So between here and here, I would be using base 4 and then base 5 for 13. So I'll add up 8 and 13 for those function values. If you were doing this by hand, it would definitely be easier to factor out. So from step 1 to step 2, they are exactly equal, but it's just approximating the integral. So exactly equal to, well, actually there's a fourth that's in common between everything. So you could take out, like right here is a fourth and right here is a fourth. As long as you see that it's in common, use some algebra to help you. And then what would be left is 3 plus 3, so 6, plus 3 plus 5, so 8, plus 5 plus 8, so 13, plus 8 plus 13, so 21, and it just makes your math easier. So you come up with a quarter times 48. So if we go check our answer choices, a quarter of 48, we see 12 is up there. Okay. Now, I did show you an example, and then we looked at a table of values, and if you look at a table of values, it's going to work how we talked about. But sometimes if they've drawn you out an image, and this is an image from our speed homework back in chapter 2, you do have to go back to the idea that the bases have to come from the parallel sides. So that is, by definition, what the base of a trapezoid is. They have to be the parallel sides. Oftentimes, it's the function heights, but not always. So in this case, they didn't give you a formula for v of t. They just drew out what v of t looks like. And in this picture, your height is actually going to be vertical, and then your bases that are the parallel sides, this is going to be base 1. Hold on, sorry, the dog is up. Alright, sorry. The bases are parallel to one another. I am terrible with this pen today. So this would be base 2. So to figure out the area of this trapezoid, this area of the trapezoid would be a half from the area formula, and then your height in this case would be 20 in this picture. And then when you add up the bases, it would be figuring out how long these are. So base 2 in this picture is 24 units long, and base 1 goes from 4 to 16, so it's 12 units long. You would add up 12 plus 24. So a lot of times you use the function heights for your bases, but that's if they give you like f of x values or a formula for f of x. If they've drawn you out an image that's already a trapezoid and your parallel sides are horizontal instead of vertical, this is how it would work. So the height is figuring out that, oh yeah, that was 20 units tall from seeing these y values of 20, and then adding up the base 1 and base 2 by figuring out like how long they span horizontally. So you do have to think about it sometimes. AP is always changing stuff up on you. Okay, one last thing. So here's an AP example, and it's going back to, okay, they tell you that a trapezoidal sum overestimates the integral, and a right-hand sum underestimates. So a trapezoidal being an overestimate, that automatically tells you that F needs to be concave up. And that's just something that you are supposed to remember. Take a look at, commit it to memory. You can draw examples to show yourself that if you're connecting the dots and you're concave up for trapezoids, then you're going to overestimate. So I know it's concave up, so I can automatically get rid of B because it's concave down, C because it's concave down, and E because it doesn't have concavity. So now, so again, B was out, C was out, and E was out just by knowing it's concave up. Then they tell you that the right hand needs to underestimate or approximate. Well, go up and draw them, or it can be something that you've memorized. But if you take a look at right-hand sums, here are some right-hand sums, or here are some right-hand sums. Again, right hand just means that as you're drawing your rectangles, you use the right-hand side for the height. Which ones underestimate? A, when you are decreasing. So this tells you that F has to be decreasing. So those are those AP kinds of connections that you need to make. Okay, I realize that that was a lot. Your job today is to make sure that you're understanding the idea of all 6 of those terms. So whether they are happening at once, whether it's just asking for one of them, whatever the case may be. If I ask you for upper, you should automatically know what that means. If I ask you for midpoint, you should automatically know what that means. Where are you getting your rectangles? And so for the first 4, they were all dealing with rectangles. Upper, lower, left, and right are all dealing with rectangles. 5, midpoint, is also dealing with rectangles. It's just that you're using the middle of the rectangle for your height. And then the last thing we saw was that instead of rectangles, you could use trapezoidal sum, or you could use trapezoids, and they would be more accurate. Typically, options 5 and 6 are your most accurate area approximations. And we talked about if you have exact area, that's when we'll use the integral symbol. So your homework is split up into 2 parts, homework 1, and then in that same packet as you go through, you will find homework 2 so that you have everything you need. And the same notes packet you will need to bring back so that we can finish it up. You will have a quiz, though, on just 4.2 and 4.3 homework 1, and then you'll have a separate quiz on 4.2 and 4.3 homework 2. So you will be doing 4.2 and 4.3 homework 1 on Tuesday. That means you can ask questions about it on Wednesday, ask any final questions on Thursday, and on Thursday we will quiz that section. I really, hope to be back with you all on Wednesday. We're just going to have to see. I did finally make it to the doctor. I have some medicine. Hopefully I'm getting better. Thank you so much for your patience, and I'm sorry for the weird scheduling.